Building a complex software architecture entirely on a smartphone means operating within severe physical constraints. You are managing thousands of lines of code with your thumbs, navigating dense interfaces on a 6-inch screen. But the real limitation is the software divide. The mobile workspace is fractured into isolated silos. On one side, Termux runs your Bash-based command line tools. On the other, PyDroid handles your Python UI development. They do not naturally communicate. Throwing external SD storage into the mix adds a third layer of separation. The files you write are physically isolated from the very environments trying to execute them, locked behind competing Android permission barriers. Historically, a legacy system called BCore tried to bridge this gap. It operated as a standalone project manager, but because it remained physically disconnected from the core files, it drifted further out of sync with every new tool and update. This divided infrastructure creates a point of diminishing returns. As the number of scripts grows, the time spent manually relinking directories across different apps begins to exceed the time spent writing new code. This isolation leads directly to namespace collisions. A variable executing in a Termux bash script can accidentally overwrite an identical variable running in a Python script, simply because they share a name but lack a shared environment. The failures cascade. Modifying a single directory path on the SD card silently breaks the legacy BCore tools, because those older scripts still rely on hard-coded static routes that no longer exist. When you introduce an AI assistant, the problem multiplies. AI context generation becomes inaccurate because the assistant can only see fragments of the file system. It hallucinates paths and writes code for an environment it cannot fully access. Traditional software patches fail to solve this because the individual environments refuse to share a single source of truth. A script in Python cannot reliably ask Bash where a file is located. The system cannot be fixed with another patch or bridge script. It requires an architectural takeover to force unification across the entire device. To solve this, the file system needs to stop behaving like a set of loose folders and start behaving like a single queryable database. This requires a data format that both Bash and Python can read with zero ambiguity. Standard JSON is functional, but its bulky key-value pairs drastically slow down parsing when passing large datasets across different programming languages on a mobile processor. This diagram shows a solution called BEJSON. Here, standard JSON key-value pairs are stripped down and separated out into two parallel arrays, one dedicated solely to the fields and a separate array built solely for the values. By enforcing this structural rule, known as positional integrity, the system eliminates the need for expensive key lookups. The field index precisely matches the value index, enabling instantaneous index-based data access. Version 104DB utilizes this logic to act as a multi-entity relational database entirely inside a single file. By requiring the first field to act as a parent identifier, multiple distinct record types can exist securely within the same structure, eliminating the need for external schemas. This specific tabular format provides the lightweight engine required to connect Termux, PyDroid, and all legacy scripts under one synchronized umbrella. The unification protocol triggers the moment the system boots. The bash RC file automatically wakes up the automation manager script. The automation manager immediately executes the core environment service, which scans the physical layout of the entire mobile file system. This service translates that physical file system state directly into the central environment core BEJSON database, logging every path and directory. Next, core command executes its primary collision defense. It reads that central database and automatically generates fresh core environment source files in both Python and Bash, where every single system variable is strictly prefixed with the letters CC_. Legacy BE core services like change trackers and system snapshots are fully absorbed into the new architecture by remapping their internal logic to these newly generated prefixed variables. This automated split-second boot cycle removes the risk of configuration errors. The system synchronizes itself before the developer even types a single command. Consider a real-world stress test. A developer moves a critical project folder to a completely new location on the SD card. The central BEJSON database detects the discrepancy during the next cycle and updates its records. It then instantly rewrites all routing variables across the Bash, Python, and JavaScript environments. This leads directly into the final operational layer, the contextualizer service, built specifically to bridge the gap between the local environment and external AI. The contextualizer reads the centralized database to automatically generate modular AI context files. These files segment the system state into discrete packages regarding the environment, core policies, and libraries. By feeding these precise files to external AI tools like Gemini or Claude, the assistant gains up-to-the-second awareness of the system's rules and logic, preventing it from hallucinating non-existent file paths. The unification of B-Core into Core Command proves a specific software principle. When you stop treating an environment as a collection of loose files and start treating it as a strict database, the system transitions from a manual overhead into a predictable automated engine.